Okay, hey guys. So this is the first videos for the first homework, for the first problem in homework 3. Homework 3, just to give you guys a brief overview, is really the first true structural homework I think that you guys will be having for this semester. And there's a lot of topics that we're introducing in here. We're doing beam analysis, frame analysis, you're doing deflected shapes, moment and shear diagrams, and this is all stuff that we'll be doing for more or less the rest of the semester. So make sure that you guys really understand the topics but make sure you guys really understand the homework that we're going over now, because it's pretty much only going to get trickier from here on out. I don't want to say that to discourage you or anything, but just be aware that if this is the type of stuff that you're uncomfortable doing, please come and seek us out to get some additional help. For this first homework problem, this one is relatively straightforward. I'm just going to give you guys some tips. I'll calculate one of the reactions for you to make sure that you all know how to deal with this moment here, and I'll give you some tips to deal with this odd load down here. So first off, for this load, the easiest way I see of dealing with that load is instead of trying to find the distance that acts with or anything, just break it up into components. So you have your normal beam. Your original load is something like this, 5. You were told that it's a 3, 4, 5 triangle, so you can just break this down into a 3 kilonewton force and a 4 kilonewton force. And doing this makes the problem much easier, I think, because you don't have to worry about like finding angles and like measuring the distance between this and doing this and finding your angles. You don't have to worry about all that. So it's a lot easier if you just break it up into components. The next step, finding the reactions. I think finding the reactions in general is usually pretty straightforward, but the tricky thing with this one is applied moment, and usually this is where I see people mess up. So how you deal with that applied moment, just you only see it when you're using your moment equations. So for example, it will influence your reactions, and that's why I'm going to calculate one of your reactions for you. But if I'm trying to think of a way to show this at the same, I'll just push this offside. Just make note of these values. You should have this in front of you somewhere. If I'm going to find the reactions, I have my beam. I have a 5 kilonewton, so this is 3, 4. This is B, and this is 10 kilonewton meters. This is a roller here. So if I do the moment about B, for example, that's here. Moment about B, and let's say that clockwise is positive. And I'm just doing that because, sorry, this is 3. I could have done a counterclockwise positive. It really doesn't matter. If I do a clockwise positive, the 4 kilonewton force is acting in the counterclockwise direction, so it's negative. It is 3 meters away from B, so this becomes a 3. I have my distributed load, which is acting in a clockwise direction. This load has a value of 1 kilonewton meter. It is 9 meters long, so I have 1 times 9. The centroid of this load, because it's a rectangular load, it's exactly halfway, so it's 9 on 2. And then I have this moment at the end, this applied moment. It is a counterclockwise moment, so I just do minus 10. Note that I'm not modifying this by anything. Over here, I had a force times a distance. I had a force times a distance. This is a moment. It is a force times a distance, so I don't need to do it twice. And then I have my dy, so minus dy times 9 equals 0. And if I solve for all that, I should get that dy is equal to 37 on 18, or it's going to be equal to about 0.056. Now, normally it's easier to keep it in fractions, but because this is an unusual fraction, like if you get a fraction that's like 6 on 5, or I don't know, 8 on 7 or something, or 7 on 8, it's usually better to keep it as a fraction because you get a lot of simplification later on, and you don't have to use your calculator as much. But for something like this, I normally just keep that. It's up to you, of course. My last comment on this video, for this problem at least, is how you draw your axial force diagrams. So for your axial force diagrams, keep in mind that tension is usually considered positive. So this is your positive sign convention for axial force. What that means is that when I'm trying to draw my axial force diagram, I'm going to draw, I'm drawing my diagram on my beam. So this is A, B, and at some point in here, C and D like this. I'm going to draw whatever value I have directly on here. So this force, this 3 kilonewton force, is causing a reaction here of 3 kilonewtons. Therefore, this section of the beam is in compression. There's no axial force in here. I have 3 kilonewtons compression. This is my axial force diagram. Just 3 kilonewtons compression, 0 all the way across for the rest of it. I will let you draw your shear and moment diagram separately. And I think that's everything for this problem. Let us know if you have any questions.